Okay, welcome to today's lecture. Today's lecture is about late law. Note that at the end of this lecture, you'll be able to know or to understand what late law is. Not only that, you'll be able to determine reaction late law, orders of reactants, overall reaction order, and the value of the late constant. So pay extra attention. So what is late law? Late law simply shows how the late depends on the concentrations of what? Reactants. Or in other words, it just shows how the rate depends on the initial concentrations of what? Reactants. Note that late law does not depend on the concentrations of products because the reaction rate is being studied under conditions where the reverse reaction does not contribute to the overall rate. So let me show you an example so that you can understand whatever I'm from explaining here. So here you are having this example where you are seeing this nitrogen dioxide decomposing to form nitric oxide and oxygen what? Gas. Now here, if at all you are asked a question to determine the general form of the late law for this reaction, how can you determine the general form of the late law for this equation or reaction? How can you determine it? So here, our main area of interest is the reactants, not the what? The products, because late law is saying it shows how rate depends on the concentrations of what? Reactants, not the products. So here, if at all we are to determine the general form of the late law for this reaction, we can determine it like this. So late is equal to, just after the equal sign, you need to write the constant K, and then you need to write the reactant we are having, which is nitrogen what? Dioxide. So that's the reactant we are having, and then you need to raise it to power n, where this n is the order of the reactant, and then where this K is the late constant, and then where this is the what? The reactant you are having, which is nitrogen what? Dioxide. So this is how you come up with the late law for this equation here. Okay, so this is what I'm from illustrating there. So late is equal to, you are having the late constant K just after the equal sign, and then where this is the concentration of the reactant you are having there, and then where N is the order of the reactant. So as I was saying, this K is just the late constant, and then N is the order of the what? Reactant. So let me show you another example so that you can understand clearly. So here now, you're having another example. Now here you're having three reactants reacting to produce these products. You're having reactant A, reactant B, and reactant what? E. So here, if at all you are asked to determine the general form of the late law for this reaction here, what can you, or how can you determine it? So here, you know that you say late is equal to, just after the equal sign, you need to write the late constant K like that, and then you need to write the concentrations of the what? Reactant. So here you have in reactant A, you can raise it to power X, where this X is the order with respect to this concentration, and then we have in B, another reactant, and then you can raise it to power Y, where this Y is the order with respect to this concentration B you are seeing here. Then you are having another reactant, which is E, and you can raise it to power Z, where this Z is the order with respect to this reactant E. So this is how you can come up with the general form of the late law for this what? Reaction here. So here we just focus on the reactants, not the what? The products. So the late law for this reaction can take this form. So this is what I'm from illustrating there. I was saying late law for this, the general form of the late law for this reaction can be late is equal to, you need to write the late constant K just after the equal sign, and then you need to write the concentrations you are seeing here, and then you need to raise it to the powers. And then these powers, in other books, they use A, B, C, D. In other books, they use M, N, and P. So you can use any letters you want, but for me, I'm familiar with X, Y, and what? Z. So under this topic, I'm going to teach you how to determine X, Y, and what? Z, and how to determine the late constant, and you need to know how to go about that. So I'm going to teach you there. And then where K is called the what? Late constant, and then X, Y, and Z are small o numbers or simple fractions, and they are the late order with respect to A, B, C, and what? E. And then the sum of X, Y, Z is called the overall reaction what? Order of the what? Reaction. So as I said, I talked about these orders. These orders you are seeing X, Y, and Z. In other words, they are what? They are integers. So they can be fractions, even including what? 0. And then what you need to know is, for example, if you determined, the value of x to be 1, or maybe the value of y to be 2, the value of z to be 1, like that. When you add all this, that's what we are calling to be the overreaction order. So we are saying the sum of these three, the sum of x, y, and z, is called the overreaction order. So I'm going to show you how to determine the orders, and how to determine the rate constant, and how to come up with the overreaction order in this example that you're going to see on the next page. So let's do an example so that you can understand clearly. One is saying, given the data below, determine the reaction rate law. So the first question is asking us to determine the reaction rate law, and then B is asking us to determine the overall reaction order, and then C is asking us to determine the constant K for the reaction. The reaction has been given here. So we are having ammonium ion reacting with nitrogen dioxide ion to form nitrogen gas and water, like this. Note that our main area of interest is just on the reactants, because I said rate law shows how rate depends on the concentration of reactants, not the products, but the reactants. So the table given below here is just showing the initial concentrations of the two reactants which are here, which is the ammonium ion and the nitrogen dioxide ion. And here we are having the initial rate. So on experiment 1, we can see the concentration for ammonium ion was this. Then on the same experiment 1, the initial concentration of nitrogen dioxide was this, and then the rate was determined. The initial rate was determined like this. On experiment 2, we can see the concentration like that, and then even on experiment 3, like that. Now we know this. Okay, now that we know the information given, let's come up with the solutions. So what's the first question asking us to find? The first question is asking us to determine the reaction rate law. So the first question is asking us to determine the reaction rate law. So how can we determine the reaction rate law? So first thing, we need to come up with a general form of the rate law for this reaction here. Remember, rate law shows how rate depends on the concentration of reactants, not the products. So here our main area of interest is just the reactants. So how can we come up with the general form of the rate law for this reaction? So you know that rate is equal to, just after the equal sign, you need to write the rate constant, and then here you need to write the concentration of the reactant. So here we are having ammonium ion like that. Then don't forget the order X, and then we also have nitrogen dioxide there, like that. Don't forget the order Y, like that. But since we have managed to come up with the general form of the rate law for the reaction above, we need to determine the orders we are having here. So we are having this order X with respect to this concentration, and we are having this order Y with respect to this concentration. So now what are we supposed to do here? So for us to determine X and Y, we need to use the experiments in this table here. So we're going to use experiment 1 and 2 for us, in order for us to determine the order Y, and then we're going to use experiments 2 and 3 in order for us to determine the order X with respect to this concentration you're seeing here. After determining the values of X and Y, then we can substitute here in this same expression you are seeing here, this rate law you are seeing here, the general form you are seeing here. After replacing, then we will say that you have come up with a reaction rate rate law. So we just want the values of this. After that, we substitute, then we have determined the reaction rate law. So how can we determine here? So I'm saying we're going to use rate 2 over rate 1. Again, we are going to use rate 3 and rate 2, like this. So don't forget this. Now let's start with rate 2 and 1, so that we can determine our order Y with respect to this concentration you're seeing here. So we're having rate 2 over rate 1, like that, is equal to the general form of the rate law. We know it, that's the ammonium ion, like that. We have the order there, and we have nitrogen dioxide there, and then the order like that, don't forget, over, we're having the late constant there, and then just the same like that, x like that, and then you're having hydrogen dioxide like that, then that's our y. And then here, the data has been given for late 2. We can come here. This is late 2 here. So late 2, our initial concentration for ammonium ion has been given to be this, and then the initial concentration of nitrogen dioxide has been given to be this. Also, our initial late has been given to be this. So we can substitute in this now. So our late is 2.70 times 10 to the power negative 7 is equal to, and then what's our initial concentration of ammonium ion? So it's this one, 0.100 more. So we're going to say 0.100 more like that, and then we need to write the order there. And then what's the concentration, the initial concentration of nitrogen dioxide? It's this one here, so we can substitute there. So it will be 0.10 more like that. Then we need to write the order. And then down here we have seen that we have in late 1. So late 1 here, we just come to this late 1 you're seeing here. So this is our 1. What's our initial concentration for ammonium ion? It's this one. The initial concentration for nitrogen dioxide is this one, and then the initial late low is this one. So let's start with our initial late 1. We know that late 1 has been given here, so it will be 1.35 times 10 to the power negative 7, and then we're having the late like that. And then what's our concentration? Well, the initial concentration of ammonium ion, it's this one here, so it will be 0.100 more like that. Don't forget x, your order there. And then what's the initial concentration of nitrogen dioxide? Is 0.005 more like that. And then don't forget, this is y. So here now we need to divide. So this into that, it can go 2 times, and then we have seen this is the same as this, so you cancel, and then this 0.010 more divided by 0.0050 more is going to give us 2, and then don't forget there is a power y there like that. So here now, these are laws of indices. The bases are the same. What do? You equate the power. So this for this one to be 2 like this, which means it's having power 1 like that. So therefore, we're equating the powers. 1 is equal to y, and our order y is equal to what? 1 like that. So here we have determined for y. So y has been determined using this late 2 and late what? 1. So our value for y, we are saying, is what? 1 like that. Now let's determine for this order x here, so that we can substitute in this general form of the late law for this same reaction. So I'm sure you're clear on how I've solved for y. So let's do the same for x, so that you can understand clearly. So these things are very simple. You just have to pay extra attention. You need to get your distinction. You need to pass with your A+ in chemistry. It's very possible if you can just pay attention to whatever is happening here and ensure that you apply the concepts and study, then you definitely make it with good results. So here I'm just going to change. I'm going to say late 3 and late 2, and let's just substitute. So late 3, what's our late 3 here? Late 3, our late has been given on experiment 3. We know that our late has been given to be this, and then the initial concentration for nitrogen dioxide is this, and then the initial concentration of ammonium ion is this. So now let's just substitute. So our late is this one for 3. So we're going to say 5.40 times 10 times 10 to the power negative 7 over, what's our late 2? Our late 2 has been given to be this one, so that's 2.70 0 times 10 to the power negative 7 like that is equal to, and then here write K. What's our initial concentration of ammonium ion? We come to this table for let 3, so that's the 0.200 more like that, and then don't forget your X, and then the initial concentration of nitrogen dioxide is this one here, so it's the 0.010 more like that, and then this is our Y, don't forget the power there, and then you write over like that, so this is our over, and then here write K like that, and then your initial concentration of ammonium on let 2 is this one here you're seeing, so it's 0.100 more like that, don't forget the X, the power there, and then here your initial concentration of nitrogen dioxide ion is that one, which is 0.010 more like that, and then don't forget your Y there on top, your Y there is the power, and then you just have to divide, so this divided by that we're going to get 2 is equal to, but have you seen this is the same as this, so we just have to cancel these 2, and then we're going to say this into that is going to go 2 times, and then don't forget the power X, so the bases are the same, so you just have to equate the power, so for this to be 2, which means it's coming 1 time, so there's 1 on top there, so therefore 1 is equal to X, and we can say the order X is equal to 1 like this. So we have determined now our X to be 1 like that. So we can conclude by saying our reaction is the first order in both nitrogen dioxide and ammonium ion. Now therefore, since that we have determined this, let's substitute in the general form of the rate law now. So here what you do is you just have to replace, then we are done with the reaction rate law. So our X is just same as 1 we have found, and then nitrogen dioxide ion is equal to, it's 1. So this is the reaction rate law that we have determined, and this now that we have determined the reaction rate law, this one you're seeing here, what can be our overall reaction order? So what can be our overall reaction order? So our overall reaction order is just the sum of these 2 orders you have found here. So overall reaction order is just the sum of the orders you are having there. So we are having 1 and 1 there. We have determined already this. So our overall reaction order is 2. So this simply tells us that the reaction is the second order. So that's how you determine it, as simple as that. Okay, and then let's solve for C. How can we determine the rate constant K for the reaction? How can we determine the rate constant K for the reaction? So the rate constant K, for us to determine it, we are going to use this same rate law we have found here. So our rate, that will be the formula that we're going to use for us to determine the rate constant K, this one they want. So we're going to use this one like this, and then even if you don't indicate the powers, it's okay, because 1 is the same as this, so you can just ignore it like that, and then don't forget. So we're going to use this one here, and then we're going to make rate constant K to be the subject to formula. So how can we make that K, the rate constant, to be the subject formula? We're going to divide both sides by the ammonium ion, the concentrations we are having here, like that. Yes, then we are having this, then we're dividing both sides so that we can main with this. So we're making K the rate constant the subject formula, so don't forget. So it will be like this, and then like that, then like that, and then we must cancel that. Therefore, the rate constant K would be let, and then over the concentration of ammonium ion, like that, over the concentration of nitrogen, like that, and then here our K is equal to. Now that we have made K the subject of the formula, so what information are you going to use to substitute on the rate and the two concentration given here? Note that for you to determine K, you must use the results of the three experiments given here. If you want, you can use the results for the first experiment, if you want for the second, and if you want for the third experiment. You're going to find or come up with the same answer. So for me, I'm going to use the results for the first experiment. So I'm saying if you want, you can use the result for the second or third, you still come up with the same answer. So if I use the result for the first experiment, I'm going to use this initial concentration of ammonium here. It has been given. So this will be my initial concentration of ammonium ion, and then this will be my initial concentration of nitrogen dioxide that I'm going to use, and then I'm going to use my rate to be this one here. So let me substitute here. So my rate there is 1.35 times 10 to the power -7, and then the units are mole per liter per second, like that, over what's my concentration on the first experiment. That's for ammonium ion, that's 0.100 more, like that, and then we are having the initial concentration of nitrogen dioxide to be 0.0050, like that, more, like that. And then when you work out all this, what will be your rate? So your rate is going to give you 27, sorry, not 27, but it's going to give you 2.7 times 10 to the power -4, like that. And then what will be your units? Will be liter per mole per second, like that. So that's how you determine the rate constant. So that's it, and I'm sure we have managed to find the rate law and the overall reaction order and the value for the rate constant. So as simple as this, you are done. So I'm sure you're clear on this. Now let's do the other example, which is the last one. Okay, now let's do example 2, and I'm sure it's clear on the first example. So example 2 is saying the reaction between bromate ions and bromide ions in acidic aqueous solution is given by the equation. So we are seeing bromate ions reacting with bromide ions and hydrogen ions to give bromine and water, like that. And then the table below gives the results from 4 experiments. Using this data, determine the orders for all the 3 reactants. So they want the orders for the 3 reactants, for this bromate ion and for the bromide ions and for the hydrogen ion. And then B is asking us to determine the overall reaction order, and C is asking us to determine the value of the rate constant. And then the table is given, which is going to help us to determine this same thing, because for us to determine the orders for all the 3 reactants, we need this information from this experiment 1, 2, 3, and 4. So here it's showing the initial concentration from the bromate ions, and here it's showing the initial concentration for bromide ions, here the initial concentration for hydrogen, and the initial rate was measured, and it is given here like this. So here, how can we now determine the orders for all the 3 reactants? So for us to determine the orders of these 3 reactants, we need to come up with a general rate law for the reactants here. So we're going to come up with a general rate law for all the reactants here. So how can we come up with that? So rate is equal to, we need to write the constant K and then the concentration of the bromate ion, like that, and then don't forget the order X there, and then we need to write the concentration of the bromide ion. It can be raised to Y power, like that, and then also having hydrogen ion, like that, it can be raised to Z, that's a power. And then here, this X, Y, and Z, they are the orders they are talking about, or they are the orders they want to determine. They are asking you to determine. So here, how can we determine X, Y, and Z? So for us to determine X, Y, and Z, we can use the results from this uh, table here, from this experiment here. So for experiment 1 and 2, it will help us determine the order for X, and then experiment 2 and 3, it will help us determine the order for Y, and then experiment 1 and 4 will help us determine the order for Z, because they just want the orders for all the three what reactants. Here they're not asking you to determine the reaction rate law, but the orders first. So how can you go about that? So here, since there is no space, let me use this part here. So here, let me just write the rate law, the general rate law, so which is K. Yeah, it was having the bromate ions, which was raised to X power, and then here it was having the bromide ion like that, which was raised to Y power, and then here it was having the hydrogen ion, which was raised to Z what power. And then the first question is asking us to determine the orders for all the three what reactants. So how can we determine that? I said for us to determine for these orders, we need to use the table, the table there, the results from the experiments, from experiment 1 to 4. But for let 2, the experiment 2 and experiment 1, we can use it to determine for what? For X. So here let will be K like that, then bromate ion like that, and then X, we are going to have the bromide ion, which will be raised to the Y power, and then the hydrogen ion like that to be raised to what? Z like that. Over, we are going to have the Z constant, and then we are going to have the bromide ion like that, then X, just write it like that, the bromate, then here Y, then that's a hydrogen ion raised to Z. And then here we're going to use the information from the data given there, from the table given there. So when we come here on experiment 1, we are having 0.01, that's our initial concentration for the bromate ion, and then here the initial concentration for bromate is 0.10, that's the one you're going to use. And then here for bromate ion, the concentration is 0.10, that's the one you're going to use there, only one. And then on the rate, we're going to use 8.0 times 10 to the power negative 10. And then on rate 2, our initial concentration from the bromate is this, and then for the bromide is that, and then for the hydrogen ion is this, and the rate is that. So this is the data we're going to use. Now let's just substitute from the equation we are having. Let's substitute to our equation here. So our rate there, okay, so now that we know the information on experiment 2, let's now what? Substitute. So on rate 2, on the table there, our rate 2 is given to be 1.6 times 10 to the power negative 3 mole per liter per second, like that, is equal to, and then here what's the initial concentration of the bromate ion on the table there? It was given to be 0.2 mole per liter, like that, raised to the x power, and then the initial concentration of the bromide ion is given to be 0.10 mole per liter according to the table there. Then don't forget to raise it to the power y. And then for the initial concentration for the hydrogen ion is 0.10 mole per liter, like that. Then you should be raised to Z power, like that. And then what about on rate 1? So on rate 1, you need to come back to the table. On rate 1, you're going to use this one as the initial concentration for the bromate ion, and then the initial concentration for the bromide ion is this one, and then the initial concentration for hydrogen is this one, hydrogen ion is this one, and then the rate has been given to be 8.0, like that, times 10 to the power negative what? 4. So let's go back to the equation now, and then we substitute. So our let 1 is given to be 8.0 times 10 to the power negative 4 mole per liter per what second is equal to K, and then what's our initial concentration there? It's given to be 0.10 mole per liter, like that, X. And then the initial concentration for bromide ion is given to be 0.10 mole per liter according to the table there. And then for the hydrogen ion, the initial is given to be 0.10 mole per liter, like that. And then here you just have to divide. So here when you divide this by that, you're going to get 2, like that. And then here as you have seen, these things are the same, so you cancel them like that. And then here you divide this divided by that, you're going to get 2, but here it's raised to x power. So what do? These are, you use laws of indices, so the bases are the same. What do? You get the power. So this 2 is same as having 1 there, so 1 is equal to x. Therefore x is equal to what? 1. So we have determined the order with respect to this first concentration of bromate ion we are having here. So we need to do the same for y and what? Z. So we need to determine these two, because the question is asking us to determine the orders for all the 3 reactants, and we have just managed to determine just one order here. So let's do the same for y and what? Z. So how can we determine y and how can you determine z? So the same thing we are from doing here. So for x we have determined. Now we should determine for y. So which formula are we going to use, or which rates are we going to use according to the experiment there, the table? So for the first one, we use the rate 2 and rate 1. Now that we have determined the order x with respect to this concentration, bromate ion, which is 1, we need to determine the order for these 2 concentration here you are seeing. So we must determine the order y with respect to bromide ion, and we must also determine z with respect to hydrogen ion. So since we used the experiment 1 and 2 to determine this order x, we're going to use experiment 3 and 2 to determine what? Y. So the order y, we're going to use experiment 3 and what? 2. So here we're going to use the information given in the data table here given. So here on experiment 3, we can see that the initial concentration is given to be this for bromate ion, and then for the bromide ion, the initial concentration is this, and then for hydrogen ion is this one, and the rate is that. And then for experiment 1, it is given to be this, that. So let's just substitute now. So here on rate 3 is given to be 3.2 times 10 to the power negative 3 mole per liter per second, like that. And then let on experiment 3 is given to be 1.6 times 10 to the power negative 3, like that, mole per liter per second, like that. And then we're having K there, and then the initial concentration of the bromate ion on experiment 3 is given to be 0.2 mole per liter, like that. Then X, and then here the bromide ion is given to be 0.2 mole per liter, like that. Then the power, and then for hydrogen ion, the concentration is given to be 0.10 mole per liter, like that. And then over, we're going to write the concentration, the initial concentration of the bromate ion on rate 2 is given to be 0.20 mole per liter, like that, X. And then the concentration for bromide ion on rate 2 is given to be 0.10 mole per liter, like that. Then you're going to have your y, like that. And then the concentration of the initial concentration of the hydrogen ion is given to be 0.10 mole per liter there. and then here what do? You divide. So this divided by that, we're going to get 2 is equal to, and then here what's common here, this it's the same here, down and top here it's the same, so you cancel, and then you divide these two. What are you going to get? You're going to get 2, and then don't forget there's a power y there. What do? Laws of indices. If the bases are the same, you equate the powers, so therefore 1 is equal to y, or y is equal to 1. So the order y with respect to the bromide ion, the order y with respect to bromide ion is now what? Y is 1. So we have determined for 2, the orders for 2 reactants, we are remaining with what? Z. So how can we determine Z? And I'm sure this time you know on how you can determine Z. It's very simple and straightforward. So I don't think so if you can have challenges, and then if you're having challenges, don't hesitate to contact me. You can ask me and I'll be able to attend to you. So now let's solve for the order for y, or for z, sorry. So z we don't know here. Now we're going to use let 4 and let what? 1 in order for us to determine the order with respect to hydrogen what? Ion. So here on the table there, now let's substitute in this so that we can come up with the order for Z with respect to hydrogen ion what? Concentration. So on let 4, it is given to be 3.2 times 10 to the power negative 3 mole per liter per second, like that. And then on let 1, our rate is on experiment 1, our rate is 8.0 times 10 to the power negative 4 mole per liter per second, like that. And then this is equal to, on top there on experiment 4, our initial concentration for bromate is given to be 0.10 mole per liter, like that, raised to x power. And then the initial concentration for bromide is given to be 0.10 mole per liter, like that, x. And then the initial concentration for hydrogen ion is 0.20 mole per liter, like that, and it's raised to z what? Power, over for the concentrations for experiment what? 1. So here for the initial experiment for bromate ion on experiment 1 is given to be 0.10 mole per liter, x, like that. And then here is 0.10 mole per liter, like that, then raised to y. And then for hydrogen ion, the initial concentration is 0.10 mole per liter, like that, per liter, okay, and then raised to z, like that. Then you need to compare. So this divided by that, we're going to get this time 4, and is equal to, this is the same, this is also the same, and then this one divided by that, we're going to get 2, and then to the power z, like this. Now this one, how can you determine this z? So we can ensure that the bases are the same, so that we can equate the what? The powers. So how can we ensure that the bases are the same so that we can determine this z? So this 4, it can be written to be 2 to the power 2, and then is equal to 2z, like that. So since the bases are the same, we can equate what? The power. So 2 is equal to what? Z, or z is equal to what? 2. So our z we have determined, which is what? 2. So we have now determined the orders for all the 3 what? Reactants. So for reactant, the first reactant here, the bromate is 1. So it is 1, yes. And then for bromide is 1 also. And then the order for hydrogen ion is what? Z, like that. We have determined. Now the other question is asking us to determine the overall reaction order. So how can you determine the overall Now we have determined the orders for all the three what reactants. We started with this one, this order for X, and then we determined the order for Y, and for Z we have what determined. So if you want now to determine the reaction rate law, you can just substitute in this what rate law here you are having here. Now here the question was just asking us to determine the it was asking us to determine the what the orders for all the three what reactants. So just by doing this, then what you are done, you have determined. Now, so how can you determine the overall reaction order? How can you determine the overall reaction order? I said the overall reaction order is just the sum of the three orders you have determined here. So overall reaction order will be the sum of the three orders you are having here. So X plus Y plus what Z. So we know that our X is 1, our Y is also 1, and our Z is 2. So our order is what 4. So that's how you go about the order. And then how can you determine the rate what constant? How can you determine the rate? Okay, now that we have determined the overall reaction order, let's determine the value of the rate what constant. So how can we determine the value of the rate constant? So the value of the rate constant, we're going to use this rate law here, where we're going to substitute our X is 1, we have determined it already. Our Y, we know it's 1, our Z is 2, so we're going to substitute. So let's use it now. So let is equal to K, the rate constant, the one we're looking for, and then our X is 1. So even if we haven't indicated, we indicate, so it's okay, but you're not supposed to indicate because 1 is same as this. And then the bromide ion like that, even if it's 1 like that, and then the hydrogen ion is 2. So I'm sure you know where this power 2 is coming from. We determined it, and then our aim is to remain with the water, the rate water constant. So what can you do here? So note that for you to find the value of the rate constant K, it can be calculated from the results of any of the four experiments in the table given here. So you can use either the results for experiment 1 in order to substitute in that rate law, and then if you want, you can use the results for experiment 2. You still get the same answer. If you want, you can use for 3 and 4. So for me, I'm going to use these results for experiment 1. So my initial concentration for bromate will be this one. For bromide will be this one, the one I'm going to use, and then the initial concentration for hydrogen, and I'm going to use this one, and then my initial rate will be this one here. Okay, so I'm sure you know all that. So let's do this now. So here I'm going to substitute with my rate. My rate there, according to experiment 1, is 8.0 times 10 to the power -4 mole per liter per second is equal to the rate constant K is the one we're looking for, and then the initial concentration on experiment 1 is 0.10 mole per liter like that, and then initial concentration for bromide is 0.10 mole per liter like that, and then the initial concentration for hydrogen ion according to the table is 0.10 mole per liter like that, raised to power 2 like that. And then here you can say 8.0 times 10⁻⁴ mole per liter per second is equal to, here you can multiply all these. But okay, so here we must multiply this concentration by that concentration, and this concentration here is having power 2, so don't forget the power 2. After punching all this on your calculator, you're going to get something like 1.0 times 10 to the power -4 mole to the power 4 per liter 4. And I'm sure you know where this power 4 is coming from. When you multiply this concentration by this concentration, it's going to give you power 2 plus this power 2 you're seeing here, it's going to be 4 like that. And then your aim is to remain with this rate what constant. So you're going to say over 1.0 times 10 to the power -4 mole like that per liter, or like that. Even this side you're going to have 1.0 times 10 to the power negative 4, like that, more whole per liter 4, like that. Then when you cancel here, your concentration will be 8.0 liter to the power 3 per mole 3 per second, like that. So why has it reduced to 3 now? You know that when you're dividing laws of indices, you're subtracting the powers. So this is how you go about the let law. So, and I'm sure you're clear on that one. And then this is your task. So this is part of your tutorial sheet question, question number 3. You can determine the order of each reactant and the overall reaction order, and after that you can also write the rate law for the reaction, and after that you can also determine the rate constant K and state its what units, as simple as that. And then where you're having challenges, don't hesitate to contact me. And then lastly, if you're interested in learning, it's 100 kwacha per course. So far we are offering mathematics, chemistry, and what physics. So if you're interested, you can make some deposits in the following numbers. You have this one for MTN, the other one here is for Airtel. If you're having FNB, you can use that one, and if you're having Zanaco, you can use that one. And after making that payment, you should make sure that you send the screenshot to these WhatsApp numbers you're seeing here. And lastly, thank you for watching.